Thanks. Let's begin with a word of prayer. So, Dearly Father, we thank you for this day. We thank you for your grace, which you give so freely to us. Thank you that we don't have to rely on our own righteousness, that we can go to heaven because of your righteousness, because of your sacrifice, Lord. We thank you for that. Just pray to be with us today. Help us to glorify you, Lord, what we do. And I just thank you for these students. Pray you continue to hold them up and just encourage them to work on this class and others this semester for your glory. In your name I pray, Lord Jesus. Amen. I tell you, after grading these tests, I don't know what to think anymore. I don't know if you guys know anything. It's an empty comment because I haven't done any grading. Okay, so sorry. Is it too soon? No. Tomorrow? Will I have the test graded by tomorrow? Possibly. I don't know. We shall see. I have to make 2 tests for my other courses tomorrow, so I'm kind of occupied with, plotting against them. Grade it like Mission 4. That's funny. All right. So, guys, the next about 4 lectures I have devoted to the problem of optimization. And of course, this is Calculus 3, so we're talking about optimizing functions of several variables, right? So that's the problem. Optimization. So basically, here's the generic problem. Given some function, say f of xy, or f of xyz, etc. And given some, domain of consideration, so that's the thing. The domain, what's the domain that you would think about for f if you're trying to optimize it? I guess it depends on the nature of the problem, right? For example, you might have that the population as a function of x and y is equal to x squared plus x over y or something. For some, who knows? I mean, there's some reason that the population of Oompa Loompas is given by this formula, right? Then what would the domain of consideration be, given that this is the population of Oompa Loompas? They could be, well, y could not be 0, that's true, for this model at least. I could consider 0 Oompa Loompas, though. What is x and y? I guess it could be the population of Oompa Loompas given, the x and y don't have to be Oompa Loompas, the p is the Oompa Loompas. X and y might be, x might be metric tons of grasshoppers you're feeding to the Oompa Loompas, and y might be the temperature on Mars. I don't know. But, well, I guess this is a bad example. Sorry. I was going to say is that the p should be positive, right, or non-negative. Curses. It's not the example I wanted. P is the range. Yeah, p would be the range. You're right. Y can't be 0. Let me come up with a better example. I don't know. Here, how about this? F of xy equals to x squared plus x over y, where x is the population of Oompa Loompas. That's not I probably misspelled it. I'm sorry, Loompas. And y is the population of rabbits. All right, so I think I made the point. The point is, if you were working this problem, then yeah, I mean, x and y are populations, right? So they could be 0, they could be positive, but I don't know what a negative population would mean. Right, so from the context of this problem, the domain of f, the domain of consideration would be what? Like x and y such that what? X is greater than or equal to 0 and y is greater than or equal to 0. Of course, that I can't really throw in. I got to throw out 0, right? I mean, mathematically, that can't be there. And so how would you figure out where that function was largest or smallest? I mean, how would you analyze such a question? So that's our goal, is to be able to answer questions like that. Given some function with some domain of consideration, how do you figure out where the value of the function is largest or smallest, right? Now, it could be like this problem. What's the domain of consideration? Well, it's genuinely two-dimensional, right? Like this, right? And if you think about that, then, well, I guess what else is x is included, right? So this is included down here. So if you think about it, logically speaking, where could there be a min or a max for this kind of problem, if there was one? I mean, there's kind of two cases, right? The one case is you could have a min or max in here, right? You could have this could be perhaps an extreme value. Or you could have something down here on the edge, right? You could also have an extreme value on the edge. Yeah.
Wouldn't the point on the edge be y equals 0?
Oh, man. Thank you, Luke. I drew my picture wrong. Or there's one way to fix this.
Yes.
Okay. There we go. That hurt your head? It physically hurts you.
It just goes against everything.
I've caused disquiet in your mathematical soul. Yes. All right. I will. There you go. All is well. Almost. Almost all is well. Here, let's fix it. X, Y. All right. Now, I'm stating this problem up front to give you the big picture of what we're doing. You see, we have two distinct problems in the problem of optimization. The one problem is to find extreme values that are like on the inside of domain of considerations, right? And for these kinds of extreme values, we need to look at the theory of multivariate power series. It turns out that realm of ideas will answer this question with great generality and beauty, and very simply, too. It'd be very simple in the end, what we learn about analyzing that kind of so-called interior point. So that would be a critical point, the interior. On the other hand, on the edge, a different bag of tricks is needed. On the edge, we use something called the method of Lagrange multipliers. Or we might do something which is less elegant. We might just plug in, like restrict the function to the edge. So on the edge, you can either use method of Lagrange multipliers, which I'll be talking about today, or we can just restrict. And so, like, to restrict, if I was going to try to see, what's a typical point on the boundary here? It's just what? Zero y, right? So if you feed that into the function, you get g of y is equal to x is equal to 0, right? It's very boring here. 0 squared plus 0 divided by y. So apparently, this model that I just made up is constant on that boundary. So there's really nothing to do. Sorry. This probably won't be very interesting either for Lagrange multipliers or for restriction. It's just the function's constant on the boundary. But more generally, we could just restrict the boundary. I'll try to do that for an actual example here. So without further ado, let me tell you about the method of Lagrange multipliers. And so I'll talk about it at first in 2 dimensions, but the argument I'm giving you easily extends to 3 dimensions. So here's the problem. Given an objective function, so that's the thing we want to optimize. Let's call that f of xy. Find extremal points, extrema, for f of xy on the level curve g of xy equals to a constant. So this level curve is also called the constraint curve sometimes. So let me derive the method of Lagrange multipliers for you before I even use it. So here's a picture. We've got some constraint curve. I'll draw it in purple. You know what? I think this is actually easier to understand in 3 dimensions now that I think about it some more. I'm going to do this in 3 dimensions. So if you guys will forgive me, just this moment of indecision, add a z to both of these. What's that do? Oh, yes. Thank you. I have to also cross out the word curve and replace it with what? Surface, right? So this is a constraint surface. And so let me update my picture. So here it is. Here's my surface. G of xy is equal to some constant. And I want to find a condition for my objective function to have an extremal point. So let's assume that f of p is an extreme value of f. So in other words, assume f of p is the answer that we're looking for. What condition must be met for f as it relates to g? Right. What does it mean for it to be an extreme value of f? And that means if I took a little ball, a 3-dimensional ball around the point P, then if I look at the values of f inside that ball, the largest or the smallest of those values is just the value at the center point. It's either min or maximized at that point P, right? And all other values close to it are either smaller or bigger, all right? So suppose this is the point P here, right? And imagine taking a curve on the surface. I'll use gamma. So you got a curve on the surface, and we're going to suppose the gamma of 0 is equal to P. What equation has to be true? What equation has to be true about G of gamma of T? And I'll put a vector on it since it's vector valued, fine. G of gamma of T has to be equal to what? We've been through this before. It has to be equal to C, right? That's what it means for that to be a curve on the surface, right? It satisfies the equation of the surface. But I can differentiate this, right? I can differentiate this, and what does that give me? The gradient of G at gamma of T dotted with d gamma dt is equal to, what's the derivative of a constant? 0, right? So this shows you that if you were to study this curve, right, if you were to go along this curve and look at different points along the curve, then you've got, on the one hand, the gradient of G, right? On the other hand, you've got gamma prime of T, right? And they're perpendicular as you follow the curve, right? The gradient's always perpendicular to gamma prime of T, because gamma prime of T is tangent to the surface, right? Okay, now in particular, this is true when we put t equal to 0, right? So the gradient of g at the point P dot d gamma dt is equal to 0. Fine. Of 0. Now what else can we say? This says we haven't even tapped into the objective function yet, have we? What happens if we construct another function? Let's call it h. Let's let h of t equal to f of gamma of t. This is, think about h. It takes in a real number, and it spits back out a real number. This is a function of one variable to one variable. And think about it. Just think about what happens at t equals to 0 for the values of h. What is h of 0? H of 0 is f of p, right? So what can we say about h of 0 as it relates to other values? If you take other values close to 0 and feed them into h, what can you say about h of 0 with respect to those other values? Like, think about it. H of 0 also has to be an extreme value for the function h. Right? What you're doing is you're tracing out some path close to the point P, right? You're looking at the values of f along this curve is what you're doing. And what I'm going to tell you is, of course, the values of h are largest at 0, which corresponds to P, or smallest. It's extreme anyway. Hey, so what does that say then about h prime of 0? H prime of 0 is equal to 0 by Fermat's theorem. Calculus 1, right? If the derivative exists and it's an extremal point, it must be that you're at a place where the derivative is 0, right? And on the other hand, we can differentiate f, right? We can differentiate f. So it's also equal to the gradient of f at gamma of 0 dotted with d gamma dt at 0. Now this time, I don't get it for all time. I just get it at this one special time, right? I only get that d gamma dt. So what I have here is the gradient of f at the point P dotted with d gamma dt is equal to 0. What does this say? This says that the gradient of f at P is normal. It's normal to M, to the constraint surface. Yeah? Do you have a question, Mike? Or? Oh, okay. Yeah.
Sorry, I missed it. What is M?
Oh, I'm sorry. This is M. I just wanted to give it a name. You could, if you want me to be more precise, M is equal to the inverse image of the set containing C. It's the level surface of the constraint function. So what does this mean? How are the gradient of f and the gradient of g then related? Gradient of g is normal to the surface. Gradient of f is normal to the surface. They must be parallel or they must be collinear. So therefore, I'm going to put therefore the gradient of f is equal to some constant lambda times the gradient of g. And that, folks, right there is known as the Lagrange multiplier condition. This is a necessary condition for us to have if that point, you solve that condition, it may be that you found a point which is going to give you an extreme value. I say it may be the case because what did we do at the start of all this? Exactly. We assumed that there was a maximum, and there might not be one, or a minimum. There might not be one. The point is, if there is one, that's a condition that has to be met for it, assuming that the objective function and the constraint surface are differentiable. Yes, sir?
So if there isn't a constraint, what that means is just sort of either keep going in whatever direction or it's completely flat.
There's lots of possibilities, yeah. if there's not an answer, there could be not an answer in all kinds of various sundry ways, yeah. Hey, let's look at an example. So what I'm actually telling you, by the way, is this method can give you false positives. It might give you two values, and you might be like, oh, minimum, maximum. It might be that neither of those is a min or a max. So you have to supplement this method with common sense. Yeah.
What does gamma represent?
Gamma is just the parameterization of a curve through the point, but you notice that this point is arbitrary. I mean, this curve is arbitrary. So this actually goes to show you that every tangent vector has to be perpendicular to the gradient of g, which shows you that g is in fact in the normal to the tangent space.
So P is supposed to be at an extreme value, right?
P is the point where the extreme value is attained. The extreme value is f of p. Yeah. I have not tried to plot that. I guess you could, well, I'll shut up. Yeah.
And the capital G is the same as the lowercase g, essentially, right?
Oh, did I start using oh, man. Oh, golly. So sorry. That was supposed to be lowercase g. I guess I could just say g equals g and be done with it. Yes, sir. Why?
Because f of p is an extreme value.
But why would that be?
Because like max is derivative of 0.
But gamma prime of 0 is a tangent vector to a curve.
But isn't the tangent vector f of max and an extreme 0?
No?
No.
No.
Okay. That's how
No, I mean, what is f geometrically is a family of level surfaces here. And this is picking out the highest or the lowest level surface which intersects with g. Like if you also want to picture what's going on geometrically with f, it's kind of, well, let me do some examples and we'll get back to your question maybe in 2 dimensions where it's easier. Yes, sir.
In your box answer down there, what's the symbol just to the right?
It's a constant. It's called the Lagrange multiplier. It's lambda. So here, let's work a relatively simple problem to get started. You got a plane. You got a point off the plane. So let's say the plane is x plus 2y plus 3z. And I want to find the point on the plane which is closest to, I need a point off the plane, so it's equal to 0. I'm going to use the point 3, 2, 1. Hopefully that's not on the plane. Yeah, it's not on the plane. Find the point on the plane closest to that point. So what's my objective? Now, first of all, there is another way to solve this problem, and that other way I taught you before is in fact faster and easier than what we're about to do. I will admit that, but this is still a good example to show you the method, all right? What was the method we learned before to solve this problem? You find the normal line to the plane and just see where it goes to. But let me show you here how to do this with Lagrange multipliers. It's a good example. So my objective function is this distance, right? So I want to look at an arbitrary point, let's say x, y, z here. And my objective function, what I want to make small, is x minus 3 quantity squared plus y minus 2 quantity squared plus z minus 1 quantity squared. That's the squared distance from the point off the plane, right, to the plane. And so what Lagrange multiplier says is I should look at the gradient of f. Oh, what's my constraint? What's the g? This is the g, right? The plane is the constraint. So I look at gradient of f is equal to lambda times the gradient of g, and I try to find if I can solve these solve these equations that result. That's not quite the whole truth. I solve this and I solve g equals to 0 simultaneously. It's important to use both. What is the gradient of f? What? Heard of? No? Imagining it. It's here. Z minus 1. Keep hearing things. I mean, I say that this is different than the way I already taught you, but in fact, it's very quickly going to lead us to exactly the same algebra that we did to find the point of intersection of the normal line and the point off the plane. What's the gradient of g? 1, 2, 3, right? So what are the Lagrange multiplier equations? I've got to solve 2 times x minus 3 equals to lambda. 2 times y minus 2 is equal to 2 lambda. 2 times z minus 1 is equal to 3 lambda. Oh, by the way, I should tell you, as a point of professional courtesy, I'm drawing lambda backward. In fact, lambda is this. I would like to fix this and draw lambdas properly, but the time in my life when I can change the way I draw lambda has long since passed. So you'll have to deal with my backwards lambdas. By now, none of you noticed, though, huh? You're like, oh, you noticed? Okay, good. I mean, sometimes it's like a new symbol, so it's like I can make it any way I want and I could draw some entirely different symbol and call it lambda. You wouldn't know the difference, yeah.
How did you start drawing it backwards? Was it easy to see backwards?
I don't know. I don't know. I just did, and before I knew it, I'd gotten used to it. So these are the Lagrange multiplier equations. We have to solve them. The Lagrange multiplier itself is an auxiliary variable. We don't really care about it. We want to eliminate it. It's just a tool to find the answer. We also have what? We also have x plus 2y plus 3z equals to 0. So how do you solve these 4 equations and 4 unknowns? In order for us to find an interesting solution, lambda must not be 0. If lambda is 0, the method breaks down. If lambda is 0, that means that one of the gradients or the other of the gradients is 0. I'm not sure what the method means there. So I usually just divide equations. That's helpful. Like if I divide these two, I get what? Y minus 2 over x minus 3 is equal to 2. And these two give me what? Y minus 2 over z minus 1 is equal to what? 2/3. So you can take both of these and solve them for y minus 2. It's 2 times x minus 3. And it's also what? 2/3 z minus 1. Any ideas what I can do next? I don't know. Two times x minus 3 is equal to lambda. I want an equation with just one unknown, right? I have 2 unknowns in this. Let me take a step back here.
Are we solving for lambda? Is that the
We're trying to solve the equations. We do not want, we don't care about lambda, no. I don't, that's why I eliminated it. So this says what? This says y minus 2 is equal to 2x minus 6, right? In other words, y is equal to 2x minus 4. That seems like a nice equation. And this one says what? Z is equal to what? I'll do 2 steps here. Fine. Z minus 1 is equal to 3/2 of y minus 2, right? which is 3/2 of what was y minus 2? Y minus 2 was 2x minus 6. So apparently that's 3x minus 18. So apparently I have z is equal to 3x minus 17. Why did I do that? I mean, I'm trying to eliminate. So apparently I'm going to try to keep x and get rid of everything else, yeah? What did I do? Oh, I canceled the 2 incorrectly. Thank you. Very good. 9, which makes this not 17, but what? I think it's 8 because I have to add 1. I do appreciate the correction. Thank you. So everybody agree with me so far? Now, what equation haven't I used yet? I have not used the constraint equation itself. So that gives me what? I get x plus 2y. What's y, though? Well, I'll just write it out here. Now substitute into this equation. I've got x plus 2 times 2x minus 4 plus 3 times 3x minus 8 equal to 0. And that gives me how many x's? 1, 4, 9, 14x equals what? Minus 8, minus 24, 32. So x is equal to 32 over 14. Then y is equal to what? 2 times 32 over 14 minus 4. And z is equal to 3 times 32 over 14 minus 8. So we get what point? 16 over 7. You say what? 4 over 7. Trusting. It's all her fault. If this is wrong, it's on you. No? She accepts responsibility, but she doesn't seem terribly concerned. I'm not doing that. So anyway, arithmetic mistake possibly at the end aside, I don't think there is one, but if there was, I hope you can still see the idea of the method, yeah? Yay. So at least 2 of us are wrong. No. I'm just kidding. Find another problem. Again, I think it's faster to use the normal line solution, don't you? But if you get better at the Lagrange multiplier algebra, then that method gets faster. Part of the reason it seems longer is it's your first time with Lagrange multiplier algebra. Let me try this one here. This is going to be a 2-dimensional example. We're going to find the points on the unit circle in which give extreme values for the objective function, which give extreme f of xy equal to x squared minus y squared. All right. So this time, this is the g. Now instead of having a constraint surface, we have a constraint curve, right? But the method's the same. So we're going to try to solve the gradient of f is equal to lambda times the gradient of g, subject to the constraint x squared plus y squared equal to 1. The gradient of f here is easy enough. That's 2x minus 2y equals to lambda times 2x, 2y. And then what? What do we have to solve? We have 2x is equal to lambda times 2x, right? And minus 2y is equal to lambda times 2y. I guess we can probably safely divide by 2 here, right? Agree? So this gives us x is equal to lambda x and y is equal to minus y is equal to lambda y. Now, let's see here. We should rewrite this as 0 is equal to lambda plus 1 times x, right? This says 0 is equal to lambda. Oh, I'm sorry. Did I say lambda plus 1? I should say lambda what? Which one of these is minus? Which one of these is plus? The x one has a minus, right? So how do you solve these kinds of equations? The answer is carefully, right? You've got to think about the different cases. We need both of these to be 0. So what are your choices? Logic. Number 1, x could be 0. If x is equal to 0, then what else has to happen? Either lambda has to be negative 1, or y has to be 0. Can x and y both be 0? No. But we're really, again, I agree with you that lambda has to be a minus 1 since y can't be 0. But the more interesting question is, what is y in this case, right? So to figure out what y is in this case, we use x squared, 0 squared plus y squared has to be equal to 1, right? Which tells me that y is equal to plus or minus 1. So therefore, in this case, I get 2 points, right? I get 0, 1 and 0, minus 1 as possible extremal points. What's my case 2? Y equals 0, but I want to focus on one equation to break cases. So the other case would be lambda equals to 1. I agree with you that the other case, you're right also. But my point is lambda equals to 1 is the other case. You see my logic is branching off from a single equation that makes sure I don't miss things, right? Because it's an either or kind of thing. To make that 0, either lambda is equal to 1 or x is equal to 0. That covers all possible logical contingencies. Okay, so then lambda equals to 1, what's that say? Then this is 2, right? So y must be 0. And what's that say then? X squared plus 0 squared is equal to 1, which tells me that x is equal to plus or minus 1. Hence, we get 1, 0 and minus 1, 0. So we've got these 4 possible extreme points, right? So how do you decide what's the minimum and what's the maximum? So then, what we do is we check them. So we got 0, plug them back into the objective function, right? So I've got f of 1, 0, f of minus 1, 0, f of 0, 1, f of 0, minus 1. What are those equal to? you get 1 for the first two, and I get minus 1 squared or 1 squared, so I get minus 1 for the last two. So these are the max, and these are the min of that objective function on the circle. You're like, well, wait a second. How do you just told me I'm not sure the method works. How can you be sure that these are actually honest to goodness min and maxes? Well, I happen to know a theorem from advanced calculus or topology, if you like. And the theorem says the following. For a function with a compact domain, a continuous function on a compact domain attains its extreme values. Now, what's a compact domain? A compact domain is one that, remember we talked about this before, right? You can put in a box, kind of, you can bound it. It's got no fuzzy edges, and that's exactly what a unit circle is. A unit circle is not a non-compact domain. You can bound it, right? You just take a circle radius 2 is around it. So you see, our first example was rather dangerous because the plane is certainly not compact, right? Plane goes on and on and on, and yet we found the answer. But you notice in the plane we didn't find a maximum. That wasn't an accident. That's because it wasn't a compact domain, which means we don't get a min and a max necessarily. We might get neither. And common sense told us that the solution we found was the closest solution, right? So let me show you a picture of what's going on, if you don't mind. Because there's something really... Oh, I hope you... Sorry. I hope you're up to where I was. I will admit, the algebra of Lagrange multipliers will try anyone's patience at various times. That is true. Oops. Well, I guess that'll work. Doo-doo-doo. Now, I got a bunch of examples in the notes, and I'll probably project a few of these either, well, partly today and partly, come on, cursor, work. Here's a picture of what just happened. All right? The red circle is our constraint curve. All right? The green are the level curves of x squared minus y squared. X squared minus y squared equals to a constant gives you hyperbolas which either open up or down or left or right, depending on whether the constant is positive or negative. Now, if I could... Apparently, 1, 0 is positive, right? So this is where we had 1. We also had 1 over here. So those are the positive level curves. The negative level curves are down here. But you can see at the extremal points, that's where the gradient to the objective function and the gradient to the constraint function match up. And those also have to be the points where it's extreme. And that's the idea. I mean, that we derived it for surfaces because I think it's easier to understand there for some reason. But there's a picture of why we got what we got, right? Here's a stupid example of failure. Suppose you have f of xy equals to x, and it's constrained to xy equals to 1. So my objective function is just the x function. And I'm constraining it to xy equals to 1. Well, xy equals to 1 goes on and on to the left and to the right. This should have neither a maximum nor a minimum. And yet, when you look at the Lagrange multiplier equations, what do you get? Oh, you get nothing. Oh, man, that's right. This is my non-example example. This is actually an example where Lagrange multiplier equations give you nothing, and there's nothing to find. It's not what I wanted. I should remove this from the notes. It keeps wasting my time. Here's a better one. So here's a picture of what just happened. There's no place where the gradient to the x function matches up with that red constraint curve. The gradient to the red constraint curve is never x hat. That's why we couldn't solve the equations. That's why I leave the example. There's something there to learn. Anyway, if you have f of x, y equal to x, and constrain it to this one, x squared minus y squared equals to 1, right? Then you do the Lagrange multipliers, and what do you get? You end up with plus or minus 1 for x. So you get either 1, 0 or minus 1, 0 as possible solutions. And you plug it in, and you'll get 1, and you get minus 1. So you might be tempted to say, aha, well, x is maximized at 1. It has a maximum value of 1. It has a minimum value of minus 1. But of course, x is not extremal. Those are not extremal points for the x function on this curve. Not at all. Right? What is that curve? What is x squared minus y squared equal to 1? This is badly drawn, but here's 1, here's minus 1. This is x squared minus y squared equals to 1. Notice when x is equal to 0, there's no solution. So it has to open sideways. The point is, that's where the gradient to the x function is collinear with the constraint curve, but it doesn't mean anything in terms of making x maximum or minimum. From the very start of this problem, if you understand what this constraint curve is, you know x is not maximized or minimized on this curve. That's absurd. There's still some significance to these points, right? They're like local maxes and local mins in some sense on the curve, but they're not global extrema like we're looking for. So, in short, if you're going to use the method of Lagrange multipliers, to be sure you're going to attain max and min, you need to have a compact domain and a continuous function. But anyway, maybe we'll look at an example or two more tomorrow. Thanks, guys.